Greetings everyone, this is Ketan Chokkara. I'm a full stack developer and an AI engineer. Welcome to my presentation for Swiggy Builders Club. So, imagine you open a Swiggy and say, I need something quick for dinner. Behind the scenes, that simple sentence has to travel through three completely different systems: food delivery, Instamart for groceries, and Dineout for reservations. Each one speaks a different protocol, each one has different tools, different parameters, and different response formats. So, who decides where your request goes? Right now, nobody. Or worse than like hardcore if else logic. I built something that fixed this. It's called the MCP Orchestrator, and it's a smart routing layer that sits on the top of the Swiggy's MCP servers and figures out exactly where to send your request, not by keyword matching but by actually understanding the context. So, let me show you the problem. Let me break down the actual problem. Swiggy operates three distinct services through separate MCP servers: food delivery, Instamart, which is quick commerce groceries, and dine out for restaurant reservation. Each server is its own microservice. They speak different protocol dialects, they have different tools, different parameters, and different response schemas. They don't talk to each other. Now, the natural solution people jump to is just use an LLM to route everything. But here's the issue: with that approach, if you send every single request to the LLM itself, you are going to burn a lot of tokens. For example, let's say I want pizza, when time of the day alone could have told you it's food delivery at 8 p.m. You're wasting latency, you're wasting cost, and you're adding an unnecessary failure point. The real engineering challenge is not building a chatbot, it's building a routing intelligence layer that combines deterministic signals with AI understanding and does it efficiently. So, what is MCP Orchestrator? So, the MCP Orchestrator is a pluggable, context aware routing layer. Think of it as a smart traffic controller for your Swiggy services. You send a natural language request to the orchestrator. It analyzes your intent across six independent signal layers, scores each service level relevance, and dispatches your query to the correct backend. And here's the key: it does this with zero hard coded logic. Everything is data driven and configurable. The code base has 15 modules by far, with zero circular dependencies, which means every behavioral parameter is externalized to YAML configuration. Adding a new Swiggy MCP server requires exactly one plugin file and one registration clause. One file, one line, that's it. And if something breaks, also, the system never crashes. It degrades intelligently across three levels, but we'll get to that later on. I'll show you the demo how it looks and how it works now. So this is the developer CLI, and let me add some query and show you. So let's suppose I need dinner now. So it's fetched the top recommendation from the restaurants and given you the options. And let's say I want to add one of these. Add one. The item is added to your cart, and by confirming it, the order is placed. And you can see it routed the server to food server, and we can track it also, like track the order. The tracking is also working good, like there is a status preparing delivery already assigned, estimated time is also 15 minutes. Let's add something another, like reserving a reservation query, like reserve for two. As you can see, the table reserved at Windmill Craftworks gets to date time and confirming booking, yes or no. We confirm this, yes, and the booking was confirmed. And you can also track this, track my, we say that Dineout booking confirmed, and it routed server to Dineout, and the third server, which is Instamart, right? So let me type one query like I need some breakfast. So it provide you the options like tone milk and eggs. Let me add one of these. So Instamart cart has been added. Delivery 29 rupees. Total is 84. Confirm the pack placing this order. We confirm this. Success. We can track this order. Yeah, you can track this order by status out for delivery. Estimated time is 8 minutes. So the routing, the router to server is Instamart. So it's working on 3 different routes: Instamart, food, and uh, uh, reservation. Right now we reserving a seat, reserving a table, right? So right now we exit and we'll get back to the documentation. So there is a plugin architecture. Let's talk about it. Yeah, there is a plugin architecture in the code base. It's called plugins, and we have Dineout, Food, Instamart. As we have 3 MCP servers, for each MCP servers we have created three plugins files. And let's talk about how this service plug into this. I used a plugin factory pattern with a central registry. Each service, food, Instamart, Dineout, is a single plugin file. This plugin registers itself with the orchestrator as startup. It declares what tools it supports, what parameter it expects, and how to format the response. The beauty of this design is the composition root pattern, and all the wirings happen in one place, which is initial orchestrator. There are no import time side effects anywhere else in this code base. No circular imports, no hidden dependencies. Every module has a single responsibility and a clear dependency direction. So if Swiggy adds a fourth service tomorrow, say Swiggy Jenny, or maybe another one, so you can create one new plugin file, register it over here, and the orchestrator immediately starts scoring it alongside the other three. No change to the core routing logic. And the sixth layer is the sixth layer scoring pipeline, which is this. And now this is the core of the system. The scoring pipeline, every request that comes in goes through these 6 independent layers, and each layer adds or subtracts points from each service score. Level 1, like time of day scores, from waits.yaml. Morning Instamart gets boosted because people buy groceries in the morning. Dinner time food delivery gets the highest score. Late night food delivery still wins. These are the configurable base scores, not hardcore logic. uh, these are the weights which I'm talking about, the 6 layer scoring pipeline. And there is a location adjustment also. If you are at the office, Instamart gets a small penalty. If you are at the gym, Instamart gets a boost. Makes sense, right? You're more likely to grab a protein shake from Instamart rather than order a full meal to your gym. Hunger level uh, hunger level, if you say you are starving, food delivery gets a boost. If you just browsing, Dineout gets gentle nudge because you might want to plan ahead. And order history, this is where it gets interesting. The system looks at your last 20 order, but it doesn't treat all orders but it doesn't treat all orders equally. The most recent 5 orders get 70% weight, and the all older ones gets 30%. This blended recency signals mean the system adapts quickly if your behavior changes. Layer 5, which is derived preferences. This is the self-learning part. The system analyzes your last 30 orders to find patterns, your most used services, your peak ordering time, your favorite cuisines. If you order Instamart every Sunday morning, the system remembers that. It gives a loyalty boost to Instamart on Sunday mornings. The layer 6, which is the LLM intent classification. Finally, the actual AI. The LLM gets the user query plus all the context we gather, and it classifies the intent. But here's the smart part: the boost from the LLM is scaled by its confidence score. High confidence equals full boost, low confidence equal partial boost. The system never blindly trusts the AI. All scores get clamped between 0 and 2, and the highest scoring service wins. The entire pipeline runs in under 500 milliseconds. So, everything I just described, every score, every boost, every penalty, lives in one file, weights.yaml. The file is the brain of the file is the brain of the scoring pipeline. It decides which service to route your request to: food delivery, Instamart, or Dineout. It contains time of day base scores, location adjustment, hunger adjustment, signal weights, and intent boost value. The important distinction here: weights weights.yaml scores which server to route to, not which product to recommend. The LLM inside each individual MCP server handles product recommendation. The orchestrator job is picking the right server at the time. And if I can show you the settings.yaml, handle the infrastructure side, which LLM providers to use, what model, API keys, database paths, server configuration, everything that an engineer would need to tune without ever touching the Python code. And the orchestrator uses a SQLite database called orchestrator.db, um, and it has three tables: address, order, preferences. As you can see in the screen, these are the tested ones. The address table stores your saved location: home, gym, office, each with coordinates and a label. The order table saves your every order you place, which server it went to, I mean, which server is went to, and what you ordered, how much you spent, and a timestamp, everything. The coolest part about this system actually learns over time. Every order gets saved, and this function called get derived preference analysis. I will show you the code base. Is wait. Yep, this is the function we are talking about, and the coolest and analyze your last 30 orders to find patterns. Your most used services, peak ordering times, top cuisine, ordering day patterns. So if you order Instamart every Sunday morning, the orchestrator already knows even before you finish your sentence. Zero retraining, zero manual tuning, it just learns through it all. And the second most thing, the LLM part, which we are talking about. The LLM layers uses Grok for intent classification, Grok model, and it is designed to be a minimal around 120 tokens, 120 output tokens per request, and temperature is set around 0. 0.1 for deterministic results, and the structured JSON response with a label, reasoning, and confidence score. The LLM doesn't just get user query, it also receives all the context we gather: time of day, day, location, hunger level, and the user's preferred service from the derived preference. This makes the classification significantly more accurate than a raw query classification. And if the LLM is down, the system falls back to the context only scoring layers 1 through 5 still run. You lose the AI nuisance, but the routing skill still works based on the deterministic signals. The user might not even notice that. And these are the three level of graceful degradation. This is something which I created. This system has three levels of graceful degradation. It never crashes, it degrades intelligently. So there are three levels: level 1, level 2, level 3. Level 1 is called full mode, all 6 scoring layers active including LLM classification. This is the premium experience a user can have. Level 2, if an LLM goes down, the LLM calls fails or times out, the system catches the exception, fall back to the 5 deterministic layer: time, location, hunger, history, preferences, still very good for routing purpose. And the level 3 where database gone down, even the SQLite database is unavailable, the system uses the seed address and defaults from config. It still routes, maybe not personalized but functional. At every level the system degrades to a non-good state rather than throwing an error. This is a production grade resilience, not a hack. And let me show you the architecture of whole system, how it looks like, from the entry point to infrastructure, the orchestration core, and the service plugins we have used in. 15 modules are there in the code base with zero circular dependencies. I built this with a strict bottom up dependency chain. Memory depends on nothing, LLM client depends on nothing, prioritizer depends on LLM and memory, but they don't depend back on it. Router depends on prioritizer, not the other way around. This build order is deterministic. You can compile the entire project in a single pass because there are no circular imports anywhere. Zero hard coded restaurant IDs, item IDs, or keyword based routing in any production path. Every behavioral parameter lives in YAML. You can completely change the scoring behavior without changing a single line of Python. And the MCP protocol uses JSON RPC 2.2 with full tool discovery, execution, and response pipeline, including an auth callback flow for Swiggy authentication. So, to summarize, the MCP orchestrator solves a real problem. How do you intelligently route natural language requests across multiple backend services without hard code everything? It does with a 6-layer scoring pipeline that combines deterministic signals, user behavior learning, and LLM intelligence. It's configurable through YAML, not code changes. It self learns from user behavior and it never crashes, it just degrades. Adding new service, one plugin file, one registration call, that's it. So, thank you for watching this video. I hope you like it. We'll meet soon.